We present DeWand, Distortion-Aware Selection Using Neural Mesh Parameterization by Richard Liu, Noah Meigerman, Vova Kim, and Rana Hanoka. Mesh parameterization computes a map from the 3D mesh to the 2D plane. This map is useful for many applications, such as detail transfer, remeshing, and texture mapping. DeWand is a technique for segmenting a mesh conditioned on the user selection for parameterization. We show an example application for segmenting and stylizing a mesh using an image texture. We take a data-driven approach, where our network takes as input a triangle mesh and a user selection, and predicts a distortion-aware segmentation. We achieve this through a novel technique we dub probability-guided parameterization. We also introduce a method for generating a data set of shapes with near developable decompositions. Our technique allows for arbitrary generation of shapes with widely varying geometry. The key objectives of segmentation for parameterization is to maximize the size of the local region while minimizing distortion of the resulting map. This is a difficult problem because the objectives are contrastive. Distortion increases with segmentation size, so the problem is ill-defined. Due to these difficulties, we take a neural approach. Prior attempts at solving this problem have relied on heuristic surface analysis to approximate the parameterization distortion. These heuristics fall flat with complex surfaces because they are either too conservative and unable to navigate around high curvature boundaries, or are too greedy and include them in the segmentation, resulting in heavy distortion. On the other hand, DeWand is capable of both identifying large developable segments and navigating around high curvature regions through distortion-aware segmentation. Our DeWand neural framework involves a fully convolutional mesh UNet model, which takes as input a triangle mesh and user selection point on the surface and predicts a latent code per triangle. These latent codes are then passed into a mesh segmentation MLP, which predicts segmentation probabilities per triangle conditioned on the selection point. Now this begs the question of how we're supposed to train this neural pipeline, and the problem is that there does not exist any labeled data for the specific task of mesh segmentation for parameterization. We take a two-pronged approach to deal with this. First, we develop a custom synthetic dataset to train our model. Starting from simple primitives with known developable decompositions, we apply deformation and CSG operations to generate new shapes with highly variable geometries. Please see the paper for further details. Despite the high variance in geometry, the synthetic dataset doesn't really capture the distribution of natural shapes. To overcome this, we additionally develop a method for training on natural shapes without labels through a self-supervised training approach we call probability-guided parameterization. The key to this approach is to pass the network-predicted segmentation probabilities as weights into an existing parameterization method. The method we choose to adapt is least squares conformal maps, also known as LSCM. We weight the per triangle expressions in the LSCM energy functional using the network predictions to derive a novel energy functional we call WLSCM. We solve a least squares problem to get the corresponding energy minimizing parameterization. In short, WLSCM enables us to compute the parameterization corresponding to the segmentation probabilities differentiably and supervise the model with the resulting distortion energy during training. To theoretically ground our probability-guided parameterization method, we prove that as the predicted weights converge to a binary segmentation, that the solution to weighted LSCM exactly equals that of the original LSCM method. We visualize this first by comparing the UV parameterizations between LSCM and WLSCM on a mesh composed of 3 sides of a cube, and manipulate the weights of the triangles in the outline edge. Note that when the weights are all 1, then WLSCM and LSCM result in the same UV parameterization. If all the weights are either 1 or 0, then the UVs corresponding to triangles with weight 1 are equal between WLSCM and LSCM. We further visualize this convergence in action by interpolating the weights of the triangles in the outline edge from 1 to 0 and solve the corresponding WLSCM problem. WLSCM requires nothing more than the input mesh and segmentation probabilities to compute, which allows us to train the Dewan system on a large collection of unlabeled natural shapes sourced from Thingy 10K. In order to balance the contrasting objectives of segmentation size and parameterization distortion, we rely on carefully crafted priors. Without these priors, degenerate solutions may emerge, such as segmenting a single triangle or triangle soup, which both induce trivially distortionless parameterizations. By training on both our synthetic dataset and a dataset of unlabeled natural shapes, we show that Dewan performs well over a wide range of geometries and artist-produced models. Due to the lightweight nature of the mesh CNN encoder, our model is able to produce predictions at near real-time rates. We demonstrate this through a proof-of-concept application in which users can load a mesh of their choice and visualize the local segmentations in real time. The above videos are all recorded on a consumer-grade MacBook with no GPU acceleration. To summarize, our work contributes a neural approach to generating distortion-aware local segmentations conditioned on the user selection, a method for generating synthetic data for near-developable segmentation, a self-supervised training framework which enables losses based on distortion energies from the predicted parameterization, and finally, an interactive application which users can use to segment meshes in real time. For further details, please see our project page and paper. Our full project code, data, and interactive application are publicly available on GitHub. Thank you.